Hello, yeah, continuing with circular motion questions. We're back with another aeroplane flying in a circle, as we often do. It's going at constant speed. So we've got a weight W and L is the lift force acting at right angles to the wings. Explain how the lift force maintains the aeroplane flying in a horizontal circle. Right, so we've got the vertical component is going to be equal to the weight, so that there's no movement vertically. And we're going to have that the horizontal component is going to be the centripetal force, which is going to mean that we're moving in a horizontal circle. An aeroplane has mass 1.2 times 10 to the 5 kilograms, flying it in a horizontal circle of that radius. Centripetal force is that. Calculate the speed. Right, so we're doing Newton's second law. We're doing our F equals ma, and that is going to be equal, of course, to mv squared over r, because we're moving in a circle. So we've got the force is 1.8 times 10 to the 6. We've got the mass 1.2 times 10 to the 5. We've got the radius, which is 2 times, where are we, kilometers, 10 to the 3. And that is going to be all multiplied by v squared. So let's cancel a whole load of things in these. 1.8 over 1.2 is 1.5. We'll double it to get 3. So we've got 3 times 10 to the 4. So v is going to be root 3 times 100, which is 170 meters per second, sticking to two significant figures. Right, so that was a nice little calculation. Now we've got a satellite orbiting the Earth at constant speed v, radius r. Show that the orbital period t is this. Right, there's a lot going on with this, because our force now is Newton's, going to Newton's law of gravity. We're going to have gmm over r squared. That is our force, and that is going to be equal to mv squared over r. But we've got no v in this, so I'll put the m over r. V is going to be our distance over time, and yeah, so that's fine. Yeah, so the distance over time, because we want, so we're going to have over t squared. The distance is going to be 2 pi r all squared, so that would be 4 pi squared r squared. So that's our v squared term there. Now we just need to rearrange this for t squared. So of course the m's are going to cancel on either side. We've got t squared is going to be, we've got 4 pi squared, we've got r to the 4, but we've got an r to divide by there, so that gives us r cubed, and then we've got gm on the bottom, which is exactly what they've given there. Right, last bit. Satellites used in television communication systems are usually placed in geostationary orbits. State 2 features of geostationary orbits. Right, so they're equatorial. So all of these satellites are orbiting around the equator, which means they're fighting for space a little bit. There's only so many you're going to be able to put up there. And the period of the circular motion is going to be 24 hours. So that's why they get to stay in exactly the same place, because they're moving with the movement of the Earth. Calculate the radius of orbit of a geostationary satellite. Right, okay. Right, I'm going to squeeze this in around the picture over here. So we've got our force, our gmm over r squared. That is equal to our, well, I was going to say mv squared over r, but we don't know anything about v, but we do know about the period. So I'm going to go with mr omega squared. So what do we know about omega? So omega is the angle that we've moved through divided by the time. So that's 2 pi every 24 hours. So there's our seconds in 24 hours. So we're going to need to square that. We're getting r cubed out of all of this. We're trying to work out r. So we've got r cubed is going to be equal to, let's cancel those m's again. So g, we're called g is 6.67 times 10 to the minus 11. I think, yeah, it is 11, isn't it? G times m, they've given us m over here. divided by omega squared. So we need to put all of this in, and we're going to get r cubed out of that. That's quite a lot to type in out of all of this. So, right, let's do the omega bit first. So 2 times pi divided by that, and divided by that. So we got that bit. Then we need to square that. That gives us our omega squared, which is going to be small. Do 1 over. Okay, that's got quite a big number. And then we need to multiply that by g, multiplied by 6.67 times 10 to the minus 11. Missed out the minus 11. Okay, that's that. And then multiplied by 6 times 10 to the, what is it, 24. Right, so that's the r cubed. And now do that to the power of a third gives, so r is going to be equal to 4.23. I mean, that's going a bit much, so I say put it in and then we can short it in a minute. How many zeros we got here? 7. 10 to the 7. So that is 4.2 times 10 to the 7 meters to 2 significant figures. Right, and at least that seems sensible. I mean, there's a lot of numbers typed in there, so I could easily have made a mistake with those, but it seems sensible because the distance to the moon is about 3.9 times 10 to the 8 meters. So yeah, we're getting on for, I don't know, about an eighth of the way to the moon, which seems plausible. If we were starting to get anything much bigger than that, then it's going to seem a bit nuts. But yeah, that seems fine. Quite a difficult one to put together there. That was quite a tough question, all in all. There's lots of numbers easy to make a mistake. I mean, conceptually, it's quite straightforward, but it's easy to make an error with that one. Okay, next up, we're having a state in terms of force, the conditions necessary for an object to move in a circular path at a constant speed. So we need a resultant force. So always want to mention the resultant bit. So resultant force, which is perpendicular to the direction of motion. So that's one thing we need. And then it's got to be towards the center of the circle, towards center of circle. It has to be perpendicular to motion, otherwise we're doing work against the direction of travel. You know, if you think of the work done, it's the force in the direction that the object is moving. And if we're doing work there, it's not going to be moving at a constant speed because we'll be accelerating the object along the line of the motion. So it needs to be acting perpendicularly. So we'll still be accelerating it, but we're not doing work on it. We're not, we're not going to be changing the speed of the motion. So that's what we need on all of that. Right, so what have we got? Oh yeah, so explain why this object is accelerating and state the direction of the acceleration. Right, so it's still accelerating because the direction of motion is changing. You think acceleration is the change in the velocity, and the velocity has direction in it. It's not just the magnitude. So we can keep it at constant speed, but we're changing direction of motion. And that acceleration is towards the center of the circle again. So we've got exactly the same bit there as we had in the first question, really. Yeah, of course, the acceleration is going to be in the direction of the resultant force. That's what we know from Newton's second law. Right, moving on to part B. Satellite moves in a circular orbit around the Earth at a constant speed of 3,700 meters per second. There's the mass of the Earth again. Calculate the radius of the orbit. Right, well, we did this more or less in the last question. So GMM over R squared equals MV squared over R. We want to get the radius, so cancel those M's, multiply through by this, divide by the V squared. So R is GM over V squared, so 6.67 times 10 to the minus 11 times 6 times 10 to the 24. divided by 3700 squared. So we can get rid of that 11, and then we've got 4 zeros we can take there. So that's 15 zeros we've taken off. It's going to come out at a reasonable, because that 37 is going to, it's probably going to come out close to 3 and all of this with the numbers on there. But anyway, I put it into the calculator anyway. 6 times 6, 6.7 divided by 37 squared is that, and that's times 10 to the 9, and we've lost 1 2 here, so we've got 2.9 times 10 to the 7 meters. So we know that's not going to be geostationary, because we just did that in the last question and it was at 4 point something times 10 to the 7 meters. Although we'll be able to work out the period from they've given us a velocity there, but they don't seem to want that in this particular question. In order to move the satellite in B to a new smaller orbit, reducing R, decelerating force is applied for a brief period of time. Suggest how the decelerating force could be applied. Usually on a rocket you're firing an engine, and it's going to have to be firing out the opposite, the way that it's traveling, so that the force is going to be in the opposite direction. You could just chuck anything out the front. If the spaceship is moving along like this and we want to slow it down, because you've got the whole Newton's third law thing, isn't it? If you chuck something out the front, then the force that you've thrown out here is going to be equal and opposite to the force experienced backwards on the spaceship. So you can say fire a rocket or engine in direction of motion, and that will slow it down to decelerate, or to slow down the ship, or whatever we're calling it, satellite, not a ship. We're still on satellites. I'd forgotten what we were dealing with. Right, and then the radius of this new orbit is 2 times 10 to the 7 meters. Calculate the speed of the satellite in this orbit. This is just doing all of this again, but this time they've given us the radius. So GMM over R squared is MV squared over R. And what are we trying to work out? We're trying to work out the speed, right? Okay, so cancel the m's, cancel an r on either side. So g times m divided by r, and then square root it. 6.67 times 6 divided by, what's the r? 2. So we got a v squared is, so that gives us 20. We got a 24, we got a minus 11, so that's 13. And then we've got, where were we? Oh, and then that 10 to the 7 on the bottom, so that gives us 10 to the 6. So yeah, we're just going to be square rooting that. So that would be a 10 to the 3, and the root of 20. Square root of 20 is 2 root 5. So 2 root 5 times 10 to the 3, roughly. The root 5 is pushing it a bit, so I've rounded it to the 20. So square root of that, 4.5 times 10 to the 3, so 4500 meters per second to 2 significant figures. So that's just, it's weird that they've asked us to do more or less the same thing in B and C for the calculation, exactly the same equation, one for R and one for V. But hey ho, I suppose it's 3 marks. But yeah, that wraps that one up. There's I suppose a few little conceptual things, but all the stuff that you have in well, not all the stuff, but a lot of the stuff you have in space is around this Newton's third law idea of throwing things out in one direction propels the other object in the other direction. We've got this continual conservation of momentum going on. So yeah, and you get the same for speeding it up. Throwing the mass out of the back which is more what we're doing by having a propulsion engine. You're throwing mass out of the back of the rocket. So if you've got momentum going in one direction, then you've got an increase in momentum in the other direction. So these things have to balance out. This is what Newton's third law is all about. Our conservation of momentum, our equal and opposite impulses on objects. So this is all how our deceleration and acceleration works in space. You can just see it more directly because we don't have all of these losses going on all the time. Obviously, we don't have this on Earth. You chuck something away from you and you don't suddenly start moving because you're held in place by friction and such like. You just get to see it when you're in space, and we've taken the losses away. Right, that was nice. So that's wrapped up another couple of questions on circular motion. I'll move on to oscillations next, I think.